C.V. Raman on February 28. For his discovery, C.V. Raman was awarded the Nobel Prize in 1930. The first National Science Day is observed on 28th February 1987. This day is celebrated to spread a message about the importance of science used in daily life of the people. When we talk about Sir C.V. Raman, he was the first Indian director of the Indian Institute of Science and founded the Indian Academy of Science in 1904. The government of India honored him with the first Bharat Ratna, its highest civilian award. He was the first Asian to receive a Nobel Prize in the branch of science. The National Science Day is celebrated to appreciate the efforts of individuals and organizations. National Science Day is about the significance of scientific applications in the daily life of the people. The theme of National Science Day 2022 is Integrated Approach in Science and Technology for a Sustainable Future. This implies that science should have a positive impact on education and that learners should be more engaged in science and innovation. The topic was chosen to provide an improved understanding of current scientific problems as well as the implications of research on learning, aptitude, and profession. Now we are celebrating National Science Day. By celebrating this day, we show our dignity and respect to the famous Indian physicist C.V. Raman for his contribution in the. As students, it is our responsibility to honor the great man and his invention by contributing greatly to the field of science through innovation. I wish all the science enthusiasts and scientific zeal. Let me conclude my speech. Thank you all.
Thank you, Bhona. Now, I would like to invite Alina Abi Abraham, Chemistry Association Secretary, to give a welcome speech.
Good evening to each and every one of you present here today. It is a moment of extreme pleasure to welcome the guests who are present to attend this webinar. On behalf of the Postgraduate Department of Chemistry, St. Mary's College, Manargad, we cannot begin without offering regards to our college principal, Dr. Punankran sir. Next up, I'm profoundly delighted to welcome our resource faculty for the day, Dr. Sajid Sarkalashi, who is currently working at the Center for Continuing Education at the Indian Institute of Science, IISc, Bangalore. At the same time, I would like to convey my regards to Dr. Shibi Susan Kuriakos, the head of Chemistry Department, as well as Ms. Marina Philip and Mr. Tony Francis, the coordinators of today's event. Finally, I would like to welcome all the professors, staff members, students, and the participants present to make this event worthwhile. The schedule of the webinar will focus on the topic of silicon solar cell technology as part of our National Science Day celebration 2022. I hope this conference provides us with new knowledge. Thank you.
It was really a warm welcome, and I thank you a lot for this affectionate welcome. Education is the passport for the future. For tomorrow belongs to those who prepare for today. Education is the most powerful weapon we can use to change the world. Let us now welcome the man who doesn't need any introduction and known among all of us for his wisdom and his knowledge, our Honorable Principal, Dr. Punankran sir. I would like to invite our Principal for Presidential Address.
Good evening, everybody. Our chief guest and my dear teachers, my dear students. First of all, I congratulate Department of Chemistry as well as Institutional Innovation Council for holding a program on the day of National Science Day. I think this is a very relevant celebration that we are holding every day because, as everybody knows, science is a boon or bane as according to the approach that we are giving to the scientific innovations and scientific truths. And as you know, science, technology and engineering is closely related. And the modern life is very much depending upon science in one way or other way. Because this is an era of technology, and this technology is fully based on our scientific theories and concepts. And many of our scientific concepts and theories have been actually renovated or rescheduled because of the new advancements that happened in such areas. And new and new areas, especially frontier areas or branches, have been reporting every year for each branch of science in recent years. However, with all these advancements, we are facing serious challenges also. That is the best example is that actually we are totally incapable in front of the COVID outbreak. Because it's a very small organism, it's a virus, but I think it's not an organism at all. As according to these biologists, it's not an organism. It's just a piece of life, like a RNA or a DNA, which is encircled with a piece of protoplasm. But still, that organism, that tiny microscopic organism, is able to make the world stand still. It can actually lead to the total crumbling of the world economy. And actually, it is going on, and we are not able to overcome it fully. We don't know exactly what is going to happen in the near future in the case of COVID pandemic also. And from Europe and US, there are a lot of the people are suspecting that new epidemics or new pandemics may come out. So I think science or scientific research is very important in this era. The students are also have to attempt research. There are a lot of avenues for the students to do research in their curriculum itself, as project or short-term assignment works. But most of the students are not taking it seriously. I think the research should be a integral component of every course and curriculum, and the students should take it seriously because we need more scientists and more researchers to explore these issues as well as these challenges. So I wish a very happy and very fruitful seminar and in connection with the National Science Day. Once again, I congratulate all the coordinators and teachers and students who behind this seminar. Wish you all success, and thank you very much. Thank you.
Thank you so much, sir. That was indeed motivating and extremely informative. The most beautiful thing we can experience is the mysterious. It is the source of all true art and sciences. So, with that being said, we would like to call upon our speaker, Dr. Sajid Sarkalashi. He obtained a doctoral degree in the field of the compound-thin film solar cells at the National Physical Laboratory, New Delhi. Further, he completed 2 postdoctoral fellowship assignments. He then worked for the Bharat Heavy Electrical Limited in their electronic division, Bangalore, in the semiconductor product group. His professional experience includes the product engineering and development, manufacturing of the silicon-powered semiconductor devices, and crystalline silicon solar cells. After superannuating the general manager, he also served the company as a consultant for development and the expansion programs in the field of photovoltaics. He is a research faculty for the proficiency course of the Photovoltaic Science and Technology and Renewable Energy Source at the Center for Continuing Education in the Indian Institute of Science, Bangalore, and he participates in training programs on solar photovoltaic conductor for the engineers, students, professionals, and entrepreneurs. So without wasting time, let us move on to the webinar on the topic silicon solar cell technology. We are excited to hear you, sir. I welcome you for conducting this webinar.
Thank you, Kartika, for that nice introduction. My name is Sajid Sarkalashi, and I am your resource faculty for this particular seminar on silicon solar cell technology. First of all, let me thank the principal of St. Mary's College, Dr. Kurian, and the head of the department, Dr. Shiri Susan, for inviting me and giving me this opportunity to speak at the occasion of on the occasion of this National Science Day. I would also like to thank Professor Marina Philip and Professor Tony Francis for organizing the event in detail and showing me the way to go forward. Now, as for me, I worked as Karthika said, I worked in Bharat Heavy Electricals Limited on power semiconductor devices and solar photovoltaic products. Now, this has given me the experience and the knowledge that I gained. I'll try to share with you here during this webinar. And I think there is a bit for everyone. Although this topic is very vast, solar materials, solar cells, photovoltaics, photovoltaic modules, photovoltaic systems, and so on. It's a very vast subject, and it cannot be just covered in this 45 minutes or 1 hour. But I'm sure that whatever I say, part of it will be useful for each one of you. Now, with this, I'll try to move forward. Now, photovoltaics is not a very new subject. It's a 60-year-old technology, and it has been developed in the US Bell Labs in the 1960s. And it was primarily for spacecraft. It was developed for spacecraft because that was used as a primary source of energy in spacecraft. But eventually, there's a frenzy of development taking place in this because of its advantages as a renewable energy source and its efficiencies, increasing efficiencies over a period of time. So our main concern is that of the fossil fuels being used. It's not only expensive, but it's also causing adverse effects on the environment. So all this has prompted people to look at other sources. Wind and solar have come out right on top, especially for India. And this technology has developed substantially in the last decade or so. So the National Solar Mission has set a target, a goal for the country for about 100 gigawatts by 2022. Although we are only at about 50 gigawatts, but there's a lot of, and it has been slowed down during the last 3 years. But there is hope that it will touch the goal of 100 gigawatts by the end of next year or so. So with this, let me start my presentation. Incidentally, India is, just 1 second, let me just get the screen all right. Are you able to see the screen now?
Yes, I am able to see.
You're able to see. Okay, so I'll cover various topics. I'll bring in renewable energy as on the front end, because that gives us the backdrop of the whole technology of solar cells. So renewable energy, then we look at the sun spectrum, sun radiation, etc. We'll briefly look at the materials, semiconductor materials, and desirable properties for solar cells. And how does silicon come? Where does silicon sit? As a favorable material. We also look at silicon supply chain, how the silicon is extracted from the ore. See, silicon is not presently manufactured in the country. Only the metallurgical grade silicon is made in the country. So it's quite interesting to look at how silicon is taken out of ore in the form of a wafer. We'll look at briefly the solar cell operations, a manufacturing process for which I'll try to show a video, and of course the conclusion. Now with this, let's just move forward. First of all, it's energy. There are 4 basic forms of energy. All of us know that kinetic energy, that of motion, which is E equal to mv squared. It's one form of energy, like a moving train or a thrown stone, which carries a kinetic energy. The next is the potential energy or the gravitational energy, which is nothing but the energy required to lift, or rather, energy stored in a material or in an object. For example, water in a dam has got potential energy. is in the form of, it can be calculated as mgh, which is where m is the mass, g is the accelerating due to gravity, and h is the height. So this is the second form of energy. Third is electrical energy, which is, as you all know, it's nothing but a flow of carriers. It's a movement of carriers in a material. This sort of energy is very popular, and it can be transformed to heat, light, and motion. Different aspects of energy, different energies. And the fourth is, of course, the nuclear energy, which is bound in the nucleus, and it's also it can be manifested as a nuclear reactor, wherein energy can be obtained by breaking down uranium, or even in the sun, where fusion takes place. That is 4 hydrogen atoms combined into 1 helium atom. So both these are nuclear forms of energy. So basically, we are looking at 4 types of basic forms of energy. And out of this, the major classifications are two. I would call non-renewable energy source and renewable energy source. The non-renewable energy source is exhaustible. It means it is finite, and is polluting, and the byproducts are also difficult to handle. Now, all these the typical examples are coal-based or petroleum or nuclear and gas-based sources. These are non-renewable energy sources. Now, the renewable energy sources are regenerative, means it can be regenerated. It is non-depleting, it doesn't deplete. It is environmentally benign, and which means it's a low carbon technology and very, very safe to use, because the handling of byproducts are very minimal here. So there are many examples of this. One is solar photovoltaics, which is a direct conversion of sunlight to electricity. You have solar thermal, where sun's rays are used to heat up a medium like water, thermal conversion. Wind, of course, it is due to pressure variations in the atmosphere, and wind, biomass. Geothermal, that is the latent heat, intrinsic heat in the Earth's crust, which can be tapped by injecting water into the depth of the Earth and taking out the hot water or steam. We have tidal waves because of the gravitational pull of the moon. We have waves because of variations in temperature and wind patterns. Of course, hydro we consider the small hydro only as a renewable source. So these are the various renewable energy sources, and the new energy sources are fuel cells, ocean thermal, that is the temperature gradient between the top and bottom of the sea. Fuel cell is something where you mix oxygen with hydrogen and you get water, the reverse of electrolysis, and the energy is generated. Then hydrogen energy is a new technology. So basically, the two classifications are there, renewable and non-renewable. Now, renewable energy is where the source cannot run out, like the sun. It doesn't run out. It is a continuous source of energy. And it can be easily replaced also, like wood. When you replant trees, wood is replaced. So it is replaced and it cannot run out. It's mostly carbon neutral. No carbon compounds are produced, like greenhouse gases, and they also do not pollute the environment. And they are also obtained from flows of energy, like natural processes, like sunshine, wind, water, etc. Whereas non-renewable energies are from stocks of energy, that is coal, uranium, or petroleum, and so on, natural gas. All these are from stocks of energy, and these are from the renewable energies are from flows of energy. Now, the environmental impact of some of these fossil fuels, we can look at them. One is depletion of natural resources. You keep taking out coal or petroleum, and it's a natural resource. It is taken out of the earth, and it can cause air pollution, acid rain, and there could be toxic substances like nuclear waste and so on. And finally, climate change. Climate change is something that I would just go into a little more detail, because that's an interesting topic. Now, we have a term known as greenhouse effect. It's a very natural process. Greenhouse effect is a natural process. There is nothing abnormal about it. And it's a process by which the Earth's temperature is balanced by the atmosphere. You know that there's a natural layer of carbon dioxide and water vapor in the atmosphere, a natural background level, which prevents the heat of the earth from going out, which means the sun's radiation is coming incident on the earth, Earth gets heated up, and Earth re-irradiates some of this heat backwards into the atmosphere. But this layer protects or prevents much of the heat from going out. The result is that Earth is maintained at a very comfortable temperature of about 15 degrees centigrade. This is the average temperature of the Earth. If this level of CO2 and water vapor were not there, the temperature, average temperature would be like that of the moon, where it is minus 18 degrees centigrade. So this is a natural process. Greenhouse effect is a natural process by which this carbon dioxide and water vapor prevents the Earth from getting too cold. It's maintained at a very comfortable temperature. So this is illustrated in this picture, wherein we can see the sun's rays falling into the, incident on the Earth, and there's a water vapor and there's a carbon dioxide layer here, and this window is open so that the re-irradiated heat from the Earth, there's a balance, there's a balance of temperature balance by absorption and emission of radiation. So this is the normal case of greenhouse effect. And this is particularly comfort. It gives you comfort because the temperature of the Earth is maintained at about 15 degrees centigrade. Now, alternatively, if there are a lot of greenhouse gases like methane, ozone, carbon dioxide, etc., they block the outgoing heat from the Earth. So that means it is reflected back to the Earth, and this causes an increase in temperature of the Earth. So greenhouse gases originate from fossil fuels, burning agricultural waste, chlorofluorocarbons, etc., which is like refrigerants and so on. So excessive production of greenhouse gases can cause this temperature retention in Earth. Now, as I said, the carbon dioxide is one of the major contributors, which is obtained from, which is a byproduct of fossil fuels, burning fossil fuels. Methane gas is from agricultural activities. Nitrous oxide is from agricultural activities and fertilizer uses. And fluorinated gases is also a contributor. So all these are majorly produced by the fossil fuels and industrial processes. So the net effect is a temperature difference between between the surface of the water temperature and that of the land. This is becoming this is an anomaly now, and the width is the gap is increasing, which means there's a heating up of the Earth over a period of time from by about 1.5 to 2 degrees centigrade. It's very small, but the effect is visible, it is discernible. And this is known as the climate change. And this gives rise to abnormal floods or high temperatures or heavy tornadoes or whatever. Any changes in geographical patterns could be due to such increase in temperature. Now, we also look at what is carbon footprint. The carbon footprint is defined in terms of global warming potential in units of gram carbon dioxide equivalent by kilowatt per electricity, 1 unit of electricity that is produced. It is known as global warming potential. And this is the highest, this is documented for different technologies, energy technologies. For coal, it is the highest, 820 gram carbon dioxide equivalent per unit of electricity produced. Whereas for wind, it is the lowest, 11. 11 is the lowest, and photovoltaics or solar energy is somewhere in between, quite less, 41 and 48. So global warming index potential is highest for coal and lowest for wind. And this is a value which can be used to calculate what is the amount of carbon dioxide that's produced. So in our normal lives, we come across many of these energy materials like electricity. Suppose we use 150 units of electricity per month. It gives rise to about 1.5 tons of carbon dioxide every year. This is obtained from certain emission factors which are standard. If you use petrol, 15 liters of petrol, it's about the carbon dioxide output is about 0.413 tons. Whereas if you use diesel, it's about 0.318. And if you use liquid petroleum gas, which is our cooking gas, it's about 0.25 tons. See, the lowest comes when we use solar energy for electricity generation. It's only about 0.053, so almost a decade. Is a magnitude, 1 order of magnitude less than that of liquid petroleum gas or diesel or petrol. So this is the advantage, so low carbon footprint for solar energy. So the basic driver, the key driver for renewable energy is to switch and utilize low carbon technology sources, renewables. So this is our motivation. So in India, the achievement as on 12th January 2022, that out of total installed capacity of all sources of energy, 393 gigawatts, 104 has been from renewables. Renewables means wind, solar, and mostly wind and solar. But of course, small hydro, the geothermal is not there in the country. When small hydro and biomass, and all this put together is about 26% of the total installed capacity. And PV solar at 49 gigawatts capacity, installed capacity is about 12.5%. It's not very large, but it is significantly large. 12% of the total installed capacity of power in the country is from solar. And the states leading in this are Rajasthan, Karnataka, and Gujarat. Now we'll look at solar energy briefly before we go into the technology. Sunlight, of course, as we said, is a very elegant source of energy, which is a source of energy for heat and light. It is abundant, it is universal, and it is distributed. It's sustainable. Sustainable in the sense it will last for next generation also. We cannot entirely use it up. There's plenty for the next generation also. So that is what is meant by sustainable. It's a low carbon technology, as we have just seen. It's very benign. And it's possible to directly convert the sunlight to electricity by photovoltaics. This is the technology that we are going to look at. And this was enabled by the Semiconductor Revolution, because there has been a Semiconductor Revolution which has taken place in the world. And this is basically the silicon chips, using silicon chips, all of it is electronics. And it's a basic PN junction technology that is used in photovoltaics. And there's a high compound annual growth rate for photovoltaics, which is almost 35%, which is significantly large. And it's very common, very easy to see the amount of solar energy reaching the Earth in 1 year is almost double that of the non-renewable energy sources combined: coal, oil, natural gas, and uranium in the Earth. So that's the kind of energy that is reaching the sun. So there is plenty of energy reaching the sun, and it can be tapped. So the sun is a very hot sphere of gas, and as I said before, there's a nuclear reaction taking place inside. The temperature inside in the core is about 20 million degrees Kelvin. And on this outside surface is TS, is 6,000 degree Kelvin. This is also very large. The total power emitted by the sun is about 9.5 and 10 power of 25 watts, which is again very large. And sun, of course, is a source of light, heat, wind, rain, vegetation, and life. So basically, we have a single source, a non-depleting and an excellent energy-producing source. Now, the sun's energy, you all know that comes to us in the form of a single white light or yellow light to our eyes. But actually, it contains different wavelengths. As we can see as science students, you will be able to see that there will be different wavelengths. We call it visible part of the spectrum. The electromagnetic spectrum extends from radio waves to gamma rays, and visible falls somewhere in the middle. And the sun's rays, if you pass it through a glass prism or through water drops, you can see a number of split wavelengths. So we are going to use only these visible wavelengths. We are going to find a material that by which we will be able to use this. And what reaches this Earth's surface and what is in the space are slightly different, because the visible rays peak at about 0.5 microns, but there is a large amount of infrared rays also that is available in the sun spectrum. Now, what is in the space is different. What is in the Earth, coming to the Earth, is different, because there is a lot of absorption taking place in the atmosphere from ozone or water vapor and so on. So what is really reaching the Earth is only about 70% of the sun's radiation. Sun's radiation is, suppose, 100. About 18% is absorbed by different materials like water vapor or clouds or pollution, and scattered also. About 11% is scattered. So ultimately, you get only 70%. But this is good enough. This is much more than enough, sufficient to meet all our needs, as we mentioned earlier. Now, the intensity of the light, or we call it solar irradiance, that is watts per meter squared. This also varies with distance from the sun. For example, Mercury, which is the closest to the sun, 57 into 10 power of 6 kilometers, it gets the maximum amount of sunlight, watts per meter squared, 9,116.4. Whereas Earth, which is farther away, gets only 1353, and Pluto, which is farthest, gets very, very small amount of sunlight. But this is sufficiently large, as you will be able to see, this is sufficiently large to achieve, to have enough solar installations. So this amount is about, this solar irradiance is about 1353 watts per meter squared. It's also known as air mass 0, and it's a standard solar spectrum for space solar cells. So if you use space solar cells, this is the amount of light that it receives. Whereas if you use solar cells on the Earth, which is called terrestrial solar cells, you get only 1000 watts per meter squared, because the rest is scattered and so on, scattered and absorbed. But this is a standard value of the sunlight that is reaching the Earth, 1000 watts per meter squared. So for the key atmospheric effects considered for photovoltaic applications, we'll call it the spectral content of the incident light, which is 0.4 to 7.7 microns, which is in the visible range. The overall solar radiation, that is radiant power density that is received by the Earth, is about 1000 watts per meter squared. This can vary depending. If it's a rainy day, you don't get 1000 watts per meter squared. It will be much less. Or if it's a cloudy day, it will be much less. But this is a normal value of the radiant power density. Then the tilt angle, the angle at which the photovoltaic module is tilted to receive the sunlight, is also important. It's basically dependent on the latitude of the place. For example, the tilt angle for Thiruvananthapuram is, let's say, about 8.48 degrees, whereas that of Bangalore is about 12.97, which means the photovoltaic module will be tilted at about 8.48 in Thiruvananthapuram, because it receives much more light, or direct light. It is closer to the equator than Bangalore, where the tilt angle is 12.97. The local variations in the atmosphere also lead to different values of solar insolation. Solar insolation is nothing but the total solar energy received over a period of time. For example, the kilowatt hour per meter squared per day. So for the entire day, you receive so much of cumulative solar energy. And this is the energy that will be useful, because these solar cells have to work from morning to evening. So the maximum amount of solar insolation will help. So the four aspects of atmospheric effects, which are favorable for photovoltaic, which are useful for photovoltaic applications. We come to now materials. Materials are basically, you know that they are divided into three materials: metals, insulators, and semiconductors. The metals are the highest, lowest resistivity. Semiconductors are in between. Semiconductors have got a negative temperature coefficient of resistance, which means its carriers, the number of carriers increases with temperature or doping. Whereas in metals, there is no, the mobility falls with temperature, so the resistivity increases with temperature. Just giving you some idea about metals and semiconductors. So semiconductors, electrical conductivity can be adjusted by doping. It has got a negative temperature coefficient resistance. Its band gap is small. Electrical properties are easily controllable. And semiconductors form the basics for all power devices like transistors, thyristors, etc. Now, the band gap of a semiconductor is very small compared to that of an insulator. This is favorable because you can easily excite the electrons from the valence band to the conduction band. The band gap is the minimum energy required to excite this energy from valence band to make it free. So this is very favorable for a semiconductor. It's small, so it can be adjusted by doping or giving an energy like photons or a thermal energy to excite to make these electrons free and make it conducting. So basically, you are looking at semiconductors for this process. Now there are different combinations of materials that can be drawn from the periodic table. The group 4 is the most popular group for semiconductors, silicon and germanium, and a combination of 3 and 6 also is possible. That is, 3 is gallium, 6 is sulfur, 6 is sulfur, gallium arsenide. 6 is 3 and 5 rather, gallium and arsenide, aluminum and phosphide, all these are semiconductors which are good for solar cells. 2 and 6 also is possible. 2 is basically the cadmium and 6 is sulfur, cadmium sulfide, zinc selenide and so on. All these are semiconductors. But the most popular again remains the group 4 semiconductors, which is silicon and germanium. Now in these materials, normally all semiconductors are insulators, because at the absolute zero they are all insulators. Now you can excite electrons or provide free electrons by doping them or by heating, doping them with suitable dopants. That is the key. For example, if you add a pentavalent material to silicon, it gives an excess electron. Or a trivalent material, if you add a trivalent dopant to silicon, it gives a hole. And movement of holes or electrons is the key for all electric currents. So as I said before, if you provide an extra electron, like a phosphorus dopant, you dope silicon with phosphorus, you get an N-type semiconductor because you have an extra electron. After sharing the 4 covalent electrons of silicon with 4 electrons of phosphorus, phosphorus has got 1 extra electron, so that contributes to the electrical current. Similarly, boron has only 3, is a trivalent material, 3 valence electrons, and the lack of electron is known as a hole. So this hole provides for conduction as a p-type semiconductor. Now, if you combine two materials, you can get a p-n junction. P-n junction is one where the carriers cross over and produces a built-in field, and this field will prevent further movement of carriers. And if this p-n junction can be forward biased or reverse biased, and if it is forward biased, it acts as a forward, it gives forward current like in a diode, and if it is reverse biased, it blocks the voltage. So that's the key for all, provides the key for all electronic devices. So materials for solar cells are now categorized, or rather desirable properties are categorized into 4 major points. One is band gap energy should be sufficient. It should be, the photon energy should be able to excite electrons through the band gap, which means the band gap should be between 1 and 1.7 eV for visible spectrum. So ideal for solar spectrum is, the ideal material is the material with band gap of 1.49. You should be able to make a p-n junction out of it, because you have to draw the current out of the p-n junction. The material should have a high absorption coefficient for light in the visible region. The raw material should be abundant. It should be available in a pure form for crystalline, preferably in the form of a crystalline material to avoid the defects. And the technology, the standard manufacturing technology should be easily adaptable, like a standard semiconductor device platform. So all these 5 conditions must be satisfied before we locate a material for solar cell. Now let's look at the different materials. Between 1.1 and 1.7 band gap, we have different materials, out of which the ones that stand out is silicon, gallium arsenide, and calcium telluride. All these have got favorable band gaps. So primarily all these materials are used in solar cells: silicon, gallium arsenide, cadmium telluride, and copper indium gallium selenide. Now another requirement is it should be silicon. We choose silicon as a proven semiconductor material. Its properties are very controllable by doping. It has got an optimum band gap. It has got a high absorption coefficient. It's a stable material, and it's a universal choice because it's easily available in a crystalline form. So silicon is a very proven semiconductor material. Silicon is also the second most abundant element in the Earth crust. The most abundant element is, of course, oxygen, which is about 46.6%. The next is silicon, which is 27.7% element availability. So availability is not a problem for silicon. It's plenty available in the Earth's crust. Now, the abundance value, that is, the depletion, is not estimated for silicon. It is so large. It's the amount of silicon available in the Earth's crust is so large that it cannot be depleted. Whereas coal is 100+ years and oil is only 50 years. That is, if you keep on drawing oil from the Earth, it can deplete in about 50 years or 100 years. Coal maybe 100+ years, but silicon is available plenty. Its depletion period cannot be estimated. So all this lead to our favorite material for photovoltaics as silicon. So we'll quickly run through the silicon's production aspects. It's an ore which is available in the Earth's crust. It's a stone. It's like sand contains silicon, or quartzite contains silicon. It is converted into metallurgical grade silicon, and is then converted into a gas, which is trichlorosilane, to purify it. It's then reacted in a reactor to form polysilicon feedstock, from which crystals are drawn, and then it is sliced into wafers. So, So the first process is drawing the silicon ore quartzite from the Earth's crust or silica sand. This sand is reacted with carbon and you get metallurgical grade silicon. This is the first process. This is done in a coke furnace, and this material is silicon is very impure, 98.5%. But most of it is used in aluminum and metal industries, and about 15% is used for semiconductor industry. So basically, you get metallurgical grade silicon from the ore. The next process is conversion of this metallurgical grade silicon by reacting with HCl to form trichlorosilane. The idea is to purify this material in the form of a gas, and then you do fractional distillation of this, and you get a very, very pure form of this gas. Now, this gas is reacted or reduced in a reactor, Siemens reactor, to silicon polycrystals. It's a standard, it's a very slow process, but you can get nuggets of silicon like this, by this process. So it is done at a high temperature in a chemical reactor, and it is converted into silicon, polysilicon material. This is known as polysilicon feedstock. And this is a starting material for crystal growth of silicon. So the first process of monocrystalline crystal growth is Chokarsky method, wherein you heat this material, silicon feedstock, in a crucible. You melt it, and then you use a seed crystal into the melt. You put a seed crystal in the melt, slowly rotate it and lift it up. You get a rod, a monocrystalline silicon rod of almost 2 meters long and about 8. It's a very slow process. It takes about 2 days or 3 days to grow this kind of rod. But you can get such rods, which is almost 8 inches in diameter and 2 meters long. So this is a monocrystalline silicon rod grown by Chokarsky method. It's a standard process of growing single crystal materials. Similarly, it can be grown into multicrystalline ingot by directionally solidifying the molten polysilicon feedstock. So you get a large silicon cast ingot of this order, which is known as multi-silicon ingot. It's almost about 1,000 kg each ingot, and this can be squared, cut into small bricks. Both monocrystalline and multicrystalline materials can be cut into bricks, and it can be sawed or cut into wafers. There'll be a kerf loss by cutting because some of the materials will be lost, but eventually by cutting this you get a monocrystalline wafer or a multicrystalline square. This is a pseudo square and this is a square wafer. So these are the two types of silicon that is available, popularly used for photovoltaics. Now, monocrystalline means what? No, it has got a long-range periodic order. That means atoms are distributed equally, or rather, the distance between two atoms is always same for a very long period in the crystal lattice. So this is a long-range order. So you have very few defects in this material, and we call it monocrystalline or single crystalline silicon. Whereas in the multicrystalline material, the order is very short range. It is very, very short. For example, you have different grains forming the crystal, and the boundaries are always broken atomic bonds. So the movement of carriers is not free. There'll be recombinations at these junctions where the grain boundaries are, and this can create problems or long-term performance issues. So always the technology is centered around single crystalline material, and the efficiencies, conversion efficiencies for solar cells is higher for monocrystalline wafer compared to multicrystalline wafer. So some statistics about a solar power plant, how much of material is used. About 10 tons of polycrystalline feedstock material can give rise to 2.5 lakhs of monocrystalline silicon wafers, and 2.5 lakhs of silicon wafers go into 1 megawatt solar power plant. And 1 megawatt of solar power plant can yield about 16 lakh units of electricity per year, or rather 4,500 units per day. That is, suppose we have 5 hours in a day with sun shining, you get about 4,500 units of electricity per day. So basically, you need to use about 10 tons of polysilicon feedstock material to get 16 lakhs units of electricity per year out of 1 megawatt power plant. Some statistics. Now, the photovoltaic effect. We'll briefly look at the effect. Photovoltaic, basically, photo means force. In Greek, it is known as light, and voltage, of course, Italian scientists, after the Italian scientists, it is volta. It is of light and electricity. That is what it means, photovoltaic effect. Now, it's a result of two phenomena. One is the absorption of light on a material and generation of electron-hole pairs in a material. And the second process is the built-in potential in the material, in the p-n junction, separates the two carriers, electrons and holes, and they are collected in an external circuit. So basically two phenomena, absorption and generation and collection. So it is illustrated here. The light is incident on this material, an N-type material. It creates an electron-hole pair by freeing an electrons and holes. So electron-hole pairs are created. Absorption and generation of carriers is the first process. The second process is that those carriers are separated in this field and they move through the load. The carriers move through the load, and the load, you can have a bulb or whatever it is. So this is the process of movement of electrons through the load, that is collection. It is illustrated in this figure more clearly. You have the photons producing these electron-hole pairs, and the electron-hole pairs are separated and they move through the load, lighting up a bulb in this case. So this is the p-n junction which we are talking about. Now the evolution of the photovoltaics was first discovered in 1839 by Becquerel, but that was only a photovoltage that he observed. But eventually in 1950s, Bell Labs produced these space solar cells, these solar cells. The silicon cells were produced in 1954 with an efficiency of 6%. And eventually, the current day solar cells are, of course, 21 to 22% commercial solar cells. So there's a significant development since 1950s, to reach this level. And today, or last year, about 151 gigawatts of solar installation took place in the world, and it's a very, very proven technology at the moment. The conversion efficiency can be calculated from its open circuit voltage, the voltage output of a solar cell, which is about 0.6 volts, and short circuit current, which is about 9 amps. So if you multiply this, you get the output of a solar cell, which is about 4.89 watts for one single solar cell. So a solar cell of area or size 156 by 156 mm squared can produce 4.89 watts. And the incident power of the sunlight on this area is about 24.3 watts. So the output divided by incident power gives the efficiency of the cell, which is Pmax. Pmax is 4.89 divided by 24.3 into 100 gives 20.13%. So this solar cell efficiency is roughly about 20%. Each solar cell can give an output, voltage output of 0.6 volts. And the current depends on the area of the cell, and in this case, it's about 9.2 amperes. Now, the crystalline solar cell, we will just briefly describe its structure. It has got a p-type layer in the base layer, p-type silicon layer, which is boron-doped silicon wafer. It can be either mono or multicrystalline wafer, on which an n-type region is deposited. That is, the phosphorus layer is diffused at about 900 degrees centigrade, and over which an anti-reflection coating layer is deposited, which is silicon nitride coating. Silicon nitride coating is to reduce the reflection on the surface of this silicon solar cell. And finally, the contacts are deposited. A silver contact, a fine silver contact is deposited. And the efficiencies are, of course, as I said, 21% for mono cell and about 20%, 19-20% for multi-cell. So I don't know if I'll be able to run this properly. I'll just try to run a 6-minute video. Please let me know if you are able to hear this. Are you able to hear this? Are you able to hear this?
Yes, sir. We are able to hear.
Okay, good.
Sir, now the audio is mute, I think.
It's mute, is it? Are you able to see here?
BHEL's Electronics Division in Bangalore is a pioneer in the solar photovoltaic area in India, with more than 3 decades of experience and dedicated in-house R&D expertise. As part of the Make in India initiative of the Government of India, A state-of-the-art multi-crystalline solar cell manufacturing facility has been established in the electronics division in a record time of 12 months. This manufacturing facility is one among the most advanced and sophisticated facilities in the country, with robotics-based automation for wafer handling. Advanced features to ensure reliability, quality, and safety of process operation is integrated in this facility. This line has a capability to process multicrystalline wafers at a throughput of 3,000 solar cells per hour. Targeted power output of multicrystalline cell from this line is 4.38 watts per cell with a conversion efficiency of 18%. Major process steps of this line are inline acidic texturization, low pressure diffusion, inline phosphorus silicate gloss removal and back junction isolation, anti-reflection coating, metallization and solar cell testing and sorting. Inline acidic texturization station. Incoming wafers are unpacked and loaded as coin stack into wafer carriers, which is part of the loader. Automatic wafer loader picks the wafer from the carrier and places on transport conveyor, which transports them into texturization equipment in 5 parallel lanes. Wafers pass through process chemical baths inside the acidic texturization process, where isotropic etching with acid mixture is carried out. This process increases surface area of the wafer, facilitating reducing reflection of incident sunlight, which is critical for efficient utilization of sunlight. After texturization process, wafers are dried and loaded into wafer carrier by automatic unloader. Low pressure thermal diffusion. Wafer carriers from previous process are carried in trolley and loaded into the wafer handler of the diffusion furnace. A robotic arm picks up wafers from the cassettes and places them on a quartz boat in back-to-back configuration. Quartz boat with wafers is loaded into the furnace, where diffusion process takes place under low pressure using phosphorus oxychloride. In this process, P-N junction is formed by thermal diffusion in low pressure environment. On completion of diffusion process, wafers are loaded back from quartz boat into wafer cassettes by the robotic system. PSG removal and back junction isolation. Wafers are transported through process chemical and rinse baths, where PSG removal and back junction isolation process is carried out by the chemical etching process, which improves the shunt characteristics considerably over the earlier plasma etching process. PECVD, or anti-reflection coating. This process considerably reduces reflection of incident light and improves light absorption, thereby increasing solar cell efficiency. Wafer cassettes are loaded into a robotic system which picks up the wafer from cassettes and loads them into a graphite process boat. Graphite boat is transported into the PECVD or AR coating furnace. A thin film of silicon nitride coating with anti-reflection properties is deposited on the wafers in a vacuum, plasma and high temperature environment. Metallization line. Metallization line consists of 4 printers, 3 dryers and 1 contact firing furnace. Front and back contacts are printed on wafer surface in screen printing machines. Front contact pattern is printed using silver paste and back contact area is printed with aluminium and silver paste for bus bars. CCD cameras are used for wafer position detection and alignment. Separate printers for front grid lines and bus bars ensures high aspect ratio screen printing and hence higher efficiency. Screen printed wafers are dried and sintered in an infrared belt contact firing furnace where a sharp temperature profile is maintained to ensure contact adhesion. Finished solar cells come out of the firing furnace. Tester and sorter. Solar cells are tested and sorted in an automatic tester sorter. Solar cells are tested for electrical characteristics like open circuit voltage, short circuit current, power output, fill factor, efficiency, etc., and sorted according to the power output narrow bands and loaded into the pre-assigned bins for respective power output. The solar cells produced in this line will be used for manufacture of high-efficiency photovoltaic modules of power output up to 320 watts using 72 numbers of solar cells. The modules shall be used in grid interactive solar power plants for energy generation all over the country. BHEL is ready for the future with its ultra-modern solar cell line.
Sorry, we'll just go back to the. So can you hear me?
Yes, sir.
Yeah.
Yes, yes.
So this is the output of the solar cell line, manufacturing line, which is a monocrystalline solar cell and a multicrystalline solar cell. It would be either one of these, not both from the same line. So the monocrystalline solar cell, as I said, has a higher efficiency of 21 to 22%. Multicrystalline slightly less because of the grain boundaries, 19 to 20%. So the global share of this technology worldwide is for the silicon technology has got about 95% share of technology out of all solar cells. The monocrystalline has got 80 and multicrystalline 15%. Whereas for thin film solar cells like cadmium telluride, cadmium sulfide, cadmium copper indium gallium selenide, cadmium sulfide, amorphous silicon, etc., has got only 5% in all, which means the major technology is still remaining with silicon at the moment. And spacecraft uses multi-junction solar cells, which is from a different material. And this is very, very small amounts used in spacecraft, but very high efficiencies. So some of the prices that, just to give you an idea about the prices, a monosilicon wafer costs about 26 rupees in terms of US dollars, 0.37 US dollars. Multicrystalline wafer is half that price, 13 rupees. And the solar cell cost per watt, it's always in terms of watt. It's about 10 rupees per watt. If you look at a PV module that you normally see, you don't see solar cells, normally you see PV modules. That costs about 20 rupees per watt. And PV systems are 30 rupees per watt, which means a 1 megawatt system will cost about 3 crore rupees. So this is kind of pricing, which is given for these materials. So finally, the solar crystalline silicon technology is a very mature and proven technology. It's proven, it's got a field reliability of over 25 years, which means it is time tested for such a long period. So one can safely use it. The guarantees are also for 25 years. For the modules, the technology partners and the equipment vendors are easily accessible. It means plenty of equipment partners. Suppose you want to start a manufacturing unit, you can easily get equipment vendors. The raw materials available universally, plenty available. Although it's not available in the country, it's mostly imported from China. But there are industries in the country, which are now starting to put up silicon units, manufacturing units, silicon wafer manufacturing units. Its cost to efficiency ratio is likely to improve. It means efficiency is continuously increasing and cost is coming down. So this ratio is likely to improve. The cell technology has got about 95% global market share. So it's a very, very proven and commercialized technology, and very widely commercialized large ground-mounted utility power plants and rooftops. So this is a very, very commercial product. And that completes our presentation. And thank you for your attention. So if there are any questions, I'd like to answer them. And I can, you can give me a feedback. Sorry.
Sajid sir, thank you for your great presentation.
Yeah.
Sir, എൻ്റെ ഒരു സംശയം എന്ന് പറഞ്ഞാൽ ഇപ്പൊ നമ്മൾ സോളാർ സെല്ലിൽ നിന്ന് മാറി സിലിക്കൺ ബേസ്ഡ് സോളാർ സെല്ലിലേക്ക് നിന്ന് മാറി ഓർഗാനിക്കിലേക്ക് മാറുന്നതായിട്ടൊരു ഉണ്ടായിരുന്നു. അപ്പൊ ഏതാണ് കൂടുതൽ നല്ലത് എന്നുള്ള സാറിന്റെ അഭിപ്രായത്തില്?
See, the organic cells like perovskites are still in the laboratory. None of it has come out onto the field. For example, silicon is a very, very stable material. Silicon crystal is something that will last forever, especially monocrystalline silicon. Whereas an inorganic perovskite cell has got a lot of degrading factors. Like it'll decompose mostly in ultraviolet. See, the sun is mainly intense radiation, not only intense radiation, but it has got ultraviolet radiation, which can decompose many materials. And these inorganics or organic cells have not really come into the field so far. And they are good for research. They are extremely good for research at the moment, but not for a commercial product.
Okay. എൻ്റെ വേറൊരു ക്വസ്റ്റ്യൻ എന്ന് പറഞ്ഞാല് ഇത് റിസർച്ച് നടക്കാനുള്ള കാരണം എന്താണ് സിലിക്കണിൽ നിന്ന് മാറി?
See, you need some material to look at after silicon. See, silicon is ruling the roost now, but you see researchers, there is not much of research that can go into silicon anymore. Silicon is so well researched and well tried material that it can go as a product, but for a fresh researcher or a doctoral study, you cannot use silicon anymore. It has come to that end of its research potential. So that is why people are looking at newer materials like these perovskites or quantum dots. All these are new materials, for basic research. So basic research, it has got a lot of scope, a lot of potential. And maybe with more people getting into this materials, one day it will probably catch up with silicon, or it will really come to a stage when it can go into mass production into the field. So it has got some potential.
Okay, sir. Thank you. Students, do you have any questions? സാറിന്റെ ആക്ച്വലി ഈ ടോപ്പിക്കിലെ കുറെ ഭാഗങ്ങള് PG-യിലെ സിലബസിൽ ഉള്ളതാണ്.
Yes. Okay.
എനിക്ക് തോന്നുന്നു അവര് ഇപ്പത്തെ തേർഡ് സെമസ്റ്ററിലായതേ ഉള്ളൂ. തേർഡ് സെമസ്റ്ററിന്റെ ഒരു എൻഡോട് കൂടിയാണ് അവർ പഠിക്കാൻ പോകുന്നതെന്ന് തോന്നുന്നു. ക്രിസ്റ്റൽ സിലിക്കൺ ബേസ്ഡ് സിന്തസിസും ഒക്കെ കാര്യങ്ങളൊക്കെ വരുന്നത്.
Silicon synthesis and silicon crystal growth and all that is quite interesting. It's not available in the country. So what I have gathered is from the textbooks and I've seen few industries elsewhere globally, in Korea and Thailand, Korea and Taiwan and so on. So I have gathered this information from them and from textbooks. So it's not still available because silicon is not, purification of silicon is still not available in the country. It doesn't take place. China is the leading producer. They had no hesitation to put up silicon plants. It's a chemical. Basically, it's a chemical industry. That trichlorosilane is toxic and poisonous. So not everybody will put it up. This trichlorosilane plants, and they all require very large investments. And China was bold enough to get into that, and they virtually controlled the whole global supply of silicon chain. Even today, if China stops exporting silicon, we'll stop our silicon manufacturing here. I'm very sure. If they put an embargo on silicon wafers, India will close down on silicon manufacturing, silicon solar cell manufacturing.
Existing solar cells, life 25 years life.
Silicon is guaranteed for 25 years, but it can break down much before that, because it is not just the silicon alone. It is as a photovoltaic system, like a PV module. PV module contains a lot of other components like EVA, that is ethyl vinyl acetate as a laminate, material, encapsulant material. Then it has got a lot of bus bars, electrical connections, which can degrade with water and water vapor and corrosive elements in the earth. Then it has got electronics, it has got charge controllers, it has got a power station controls. All this can break down. So over a period of time. So it is not the silicon's life alone that matters now in the field. You require life of each and every inverter, for example, should be lasting 25 years. I don't think any inverter will last 25 years. Any electronic systems will break down much before that. So you need to have a combined life. It is not that silicon alone will contribute to this 25-year-old, but silicon supplies are guaranteed for 25 years.
ഈ കോവിഡ് സമയത്ത് കേട്ടിട്ടുണ്ടായിരുന്നു സിലിക്കണിന്റെ ഡെഫിഷ്യൻസി മൂലം ഇന്ത്യയില് മൊബൈല് അതുപോലെ ലാപ്ടോപ്പുകളുടെ പ്രൊഡക്ഷൻ കുറയുന്നതായിട്ട്. അത് ഈ ചൈനയിൽ നിന്ന് ഇറക്കുമതി കുറയുന്നതിന്റെയാണോ?
Actually, laptops and they use integrated circuits. I don't think anybody in India, very few people in India manufactures ICs. All components are coming from China, including the laptops. If you look at any laptop on the backside, you will see manufactured in China.
Yeah.
So really, I don't think India manufactures any of these primary semiconductor components. The integrated circuits all come from China or mass produced in Taiwan or China or some of these countries where people have subcontracted, cheaper countries like Thailand and so on, Ceylon or whatever. Now, the silicon chips for solar cells primarily comes from China. So if they put an embargo, as I said, we will be in trouble. I'm very sure. So to offset this and to increase our reliability, the government is now encouraging silicon manufacturing in the country. Like Adani and Vikram Solar, all these companies have now have had expression of interest for creating manufacturing facilities for silicon. So in the next, I think 5 to 10 years, I think we'll be seeing some manufacturing activity in silicon in the country.
വേറെ എന്റെ ഒരു ക്വസ്റ്റ്യൻ എന്ന് പറഞ്ഞാല് ഇന്ത്യയിൽ എവിടെയാ ഡെപ്പോസിറ്റ് കൂടുതൽ സിലിക്കൺ ഡെപ്പോസിറ്റ്? അങ്ങനെ
Karnataka, Andhra Pradesh has got the highest, I think. So you need white silicon, white sand or silicon which is white in color, not the gray one. Gray one has got a lot of impurities. White sand or quartzite. Quartzite is a very common ore which is available in Andhra Pradesh and Karnataka. I'm sure it should be available in other states also. But again, as I said, our manufacturing is limited to only the metallurgical grade silicon. That is, you just use that quartzite and convert it into metallurgical grade silicon in a coke furnace. After that, the purification into trichlorosilane and the reactor to polysilicon ingots, they don't happen in the country. There are too much chemical based industries, very, very chemical based industries.
Okay, dear students, do you have any questions?
You can also talk to me through email. I've given the email in the presentation. I'll send you a PDF of that. Maybe those who are interested, they can use it. I think you can convert it, right, Tony?
Yeah.
Professor Tony, you can record it and convert it, right?
Yeah, sure. I will do that, sir.
Yeah. So thank you again. If there are no more questions, thank you once again, Professor Marina, Philip, and Tony Francis, who guided me through the various steps of this in detail of this event. And thank you for giving me this opportunity to talk to you all. If there is any more questions, you can, of course, ask me through email or any other means. You can pass it on to me.
Okay, sir. Sure, sir. Kartika?
Thank you, sir. Once a great man is told, feeling thankfulness and not expressing it is like wrapping a present and not giving it. Now, I would like to invite Mr. Tony Francis, Assistant Professor, Department of Chemistry, St. Mary's College, Manarghat, for vote of thanks.
Good evening, everyone. As you all know, National Science Day is celebrated on every year on February 28 in India to commemorate the discovery of Raman effect, which led Sir C.V. Raman winning the Nobel Prize in 1930. Today, the postgraduate Department of Chemistry, and Institute Innovation Council jointly organized the webinar on the topic Silicon Solar Cell Technology. And this topic is one of the most relevant because of the drastic effect of climate change and the depletion of fossil fuels. And we are really grateful to have an apt person like Dr. Sajid, who has a vast experience in silicon solar cell technology. On behalf of Postgraduate Department of Chemistry, IIC of St. Mary's College, I express our sincere thanks to Sajid sir. Thank you, sir, for your valuable insights about solar cell technology.
Thank you, Professor, for those kind words. Thank you.
Also, I thank Dr. Punyan Kurian, Principal of St. Mary's College, for presidential address. I am really grateful to Dr. Shibi Susan Kuriakos, HOD, Department of Chemistry, and Professor Marina Philip, the coordinator of the event, and other teachers for their support. Also, I express my gratitude to Alina Edby Abraham, Chemistry Association Secretary, for the welcome speech. I thank Bhuvanar Pai for the knowledgeable introduction into National Science Day, and Kartika Pradeep for comparing this webinar. I would like to thank each and everyone for being here and making this event a great success. Also, I would like to see some of our PG and UG students doing their research in photovoltaics in the recent years to come. Thank you, one and everyone present here. Thank you very much. Thank you, sir, for being with us.
Okay, thank you. Thank you very much.
Thank you, everyone.
Thank you, sir.